are ready to get going this afternoon. Thanks to all of you who are showing up in person. It sounds like we've got about a dozen or more people on Zoom now, so welcome to those of you who are joining us remotely. Welcome to the Water Resources Institute's Water Connects Spring Series. We've named this series Water Connects because water connects us, and because our seminar series gives us a chance to connect with each other and new faces and people. We are calling this spring series subtitle Catamounts Catalyzing Change because we are highlighting UVM Catamounts who have done degrees here and gone on to work in water work beyond the university and are having impactful, executing impactful work out there in the real world. So we're really excited to launch this series this semester and to highlight the first of our speakers today. My name is Beverly Wemple. I'm director of the Water Resources Institute, and it's my pleasure to get to do the first introduction. So I'm happy to introduce Dr. Scott Hamshaw, our speaker for the day. Scott is a civil engineer and a water resources scientist with the U.S. Geological Survey. In his current role as a machine learning specialist, he is active in national scale research on applying deep learning methods to the prediction of water quality and water quantity in rivers across the U.S. Scott first came to UVM through a dual degree engineering program with St. Michael's College, graduating in 2006. He subsequently worked in Vermont as a consulting engineer, working on water resources engineering and site development projects throughout the state. He returned to UVM for graduate school in 2011, which is when I met him, joining the civil and environmental engineering program for a master's degree and subsequently a PhD program, with a research focus on watershed erosion and sediment transport. After completing his PhD, he was a postdoctoral associate and a research assistant professor at UVM, applying machine learning to water resource problems, as well as teaching land surveying and stormwater engineering courses. Scott joined the analysis and prediction branch of the USGS Water Resources Mission Area in 2021, and he lives in Bristol, Vermont. And we're thrilled to have him come to talk to us today about his national scale work with USGS. The talk today will last about a half hour. It will ask if you'll just hold questions to the end. We have time set aside for Q&A at the end, and then we have snacks in the corner. I would like to encourage those of you who are here in person to stick around for a little bit of socializing and networking, and those of you who are on Zoom to consider coming to campus sometime one afternoon, one day this week, so you can partake in snacks and in-person interactions with us. With that, I'll turn it over to Scott.
Thank you very much, Beverly. Great to be here. Thanks for those joining online too. Okay, perfect. There we go. I'm going to be sharing some highlights of projects I've worked on the last few years at USGS that largely kind of build around efforts for building the tools that are helping deliver kind of the next generation of hydrologic extremes data. So I'll touch on some work on water conditions and floods, as well as droughts. Just a little kind of quick overview. I was also asked as part of this Catamounts Connects series to share a little bit for my professional journey kind of post UVM. So I'll touch on that, and then talk about some tools for characterizing kind of water conditions, both high and low, and then touch on some methods for understanding flood types, so the causal mechanisms of floods, and then development of stream flow drought forecasts that have been a big part of the my work at USGS so far. And before I get started, I'm going to be presenting today the work that's really a lot of team-based science. So I want to acknowledge that I'm presenting the work that I certainly did not do alone. Different teams at USGS, including the computational tools team, the Viz Lab, data-driven drought prediction team, as well as the Army Corps and USGS joint mixed populations flood frequency team, all contributed to this effort that I'm presenting today. Okay, so my kind of professional journey from UVM involves a couple of trips back here again, and I'm pleased to be back here again. because I did my undergrad here in addition to my PhD, I'm going to jump back a little bit and start with the bachelor degree. While at UVM here as an undergrad civil engineering student, I participated in some international development engineering work in Honduras through the Community Development and Applied Economics program, as well as the civil engineering program. That kind of sparked an interest in water resource engineering that led me to a professional consulting kind of engineering role for a few years. I did based in Vermont here, worked a lot on some stormwater project work, including up at Jay Peak. Ended up just doing a lot of sort of like mountain development type engineering work, including some mountain coaster development work too, which was a little bit of a odd side path. I was interested in coming back to grad school to learn more about the kind of like methodology behind a lot of the water resource engineering work we were doing as consulting engineers. And that coincided with me returning to grad school on the very day that Tropical Storm Irene impacted Vermont, and gave like a very clear kind of like motivating issue to base my research around. So that drastic example of watershed erosion and geomorphology led me back to start the master's and PhD programs here in civil engineering. Well, here I studied a few different kind of aspects of that, both the sort of like land surveying characterization with remote sensing, the use of UAS and terrestrial LiDAR, as well as like in-stream monitoring for turbidity and applying data-driven modeling to kind of understand that data. All focused around kind of characterizing, capturing data on how quickly our watersheds were eroding and transporting sediment. Well, kind of continuing along with some of that similar research in a postdoc and research professor role here, the opportunity arose to do very similar type of applied research at USGS, remotely from Vermont here, which seemed like a kind of best of both worlds. I could stay in the applied research, continue to kind of connect with people at UVM, and kind of expand my focus research-wise beyond just Vermont. And so that has sort of looped me back in a kind of odd way back to the Water Resource Institute here, where I'm sitting over with another USGS scientist just on the other side of the door there. So we are co-located here right now, which has been a great option. So that sort of like professional journey from consulting engineering to graduate school to postdoc and research to applied research and public service. I just reflected back on a couple of the kind of like people that and maybe the more organizations that kind of helped guide me through that. And just want to mention that, I did my degree at UVM here, so UVM was a core piece of it, as well as National Science Foundation kind of provided the funding, but a few organizations that I'd say provided some key sort of like workshops and sort of opportunities that leveraged my sort of like interest in applied research with the Switzer Foundation. They provide environmental fellowships, and I was very fortunate to receive one of those. And then also some workshops offered by Kawazi and DOE's Office of Biological and Environmental Research on open watershed science. So those sort of three organizations were definitely key contacts for me that I've stayed in touch with a lot of the people in those organizations. And then, keep circling back to UVM. I've my whole time sort of here through graduate school, postdoc, research professor, and now as a USGS scientist, I've stayed in touch with many of the people that are part of the Water Resource Institute now. Thank you all for being supportive of my career and making it happen. All right, so now share some project highlights. First, a little bit of motivation on kind of like these different, these three different kind of topics I'll touch on today. One is that our existing water data and services are in need of modernization. If you're familiar with the USGS's water watch system that's been operational for about 20 years now, that is heading for retirement kind of very shortly. I think it says February 24th there. So there's a lot of our USGS systems that are in need of modernization and transition to kind of replacement services. We also are starting to see a greater need in the kind of granularity of the data that we are using. We don't so much need just information on there was a flood peak, but what type of flood was it? What are the characteristics? What's the context around that? And then finally, we're also seeing need for new data and new services in areas that are kind of high profile and high priority issues such as drought. So USGS hasn't had a lot of data specifically on drought, and that's something that we've been working on filling in and complementing existing services that are out there. So all of these projects I've had a role in more from the sort of method and tool development as opposed to building the actual websites and visualizations and those type of things. So I'll share a little bit of that work here. First, this modernization of water watch. Are most people familiar with these kind of dot maps of water conditions and have seen those? Okay, so yeah, this is water watch, and it shows sort of categorizes each stream gauge in the USGS network, whether that is kind of running much below normal, above normal, and you can get a sense of if rivers are running high or low in flood or low flow conditions. And that website is sort of in kind of very, very basic maintenance mode right now. Most of the people that created that have retired and it's in need of modernization and replacement. So our goals in this was to kind of preserve the well-tested and validated calculation of the statistics that is provided over 20 years, but adopt modern code bases, open science methods, and really document and follow like USGS fundamental science practices. Because right now it's a website where you don't have access to a lot of information about its calculations and how those are made. And we want to see if we can serve multiple user groups at the same time with doing that. So my work was involved in creating the HiSwap Python software package. And this package is meant to be a lightweight package that provides the foundation for updated water data services and statistics. So we want to replace the kind of undocumented statistics service in USGS, what they call the NWIS database, and be able to replicate the water watch system, which is no longer maintained. Additionally, USGS at the same time, or very recently, came out with a Python package that allows you to retrieve water data, data retrieval -Python, kind of similar to the R package that existed for a long time. So we wanted to integrate easily with that as well. So this package is available now. We have the open source GitHub repositories, and a lot of effort went into sort of function documentation and example workflows and validating that we can, one, recreate exactly how WaterWatch has been providing data for 20 years, but now you can see the exact calculations and tools and methods going into that. So we welcome people to take a look at that. In addition to being able to replicate that service and those calculations, because it is a Python package that's available to everyone, there's some key features that anyone can use and would welcome people trying it out. what creation of things such as flow duration curves, cumulative hydrographs, raster hydrographs, duration hydrographs, and things like that that you see here are things that are built into that package. And we're looking at possible new features, including some base flow separation and improved zero flow handling are things we might try to tackle this year. And so like, how is this kind of Python package already being leveraged? One is through web access. If you've seen, there's been a lot of changes over the last year. They're happening very regularly right now, of updates to accessing the water data through USGS's website. So replacement of that, what we call the like NWIS, or the NWIS web system with now the water data for the nation. And so these like duration hydrographs are now available online through the monitoring location pages and the updated state water condition pages. I can pull these up at the end if people want me to kind of show how to access these. But we now have a very clear documentation of the calculations and methods going into creation of these. And so these are accessible both now through the web as well as programmatically if you want to directly use the Python package. Okay. Next project I'll kind of highlight is, so on the extreme side, flood data. USGS has for a very long time provided a peak flow data record for stream gauges. So a record of the annual maximum peak stream flow that occurred over the entire, often close to 100 years of record of these stream gauges. But we often have very little or no kind of context on the type of floods associated with that. There is, if you're like very familiar with the like intricacies of the USGS database, you can get a peak flow qualifier code that says the discharge was due to snowmelt, hurricane, ice jam, or debris dam. Not especially helpful if you're trying to do a study on flood types, and that's also kind of intermittently used. The intent of that was not to describe the context of a flood. So we do need more information than that, and it's an area that has been highlighted as kind of a high priority for improving our flood frequency analysis methods. So yeah, the importance of knowing those flood types. You often have the case where different a flood peak can be caused by different storm types or different meteorological phenomena. For instance, atmospheric rivers versus kind of other types of rain events. So this is a plot of high peak flows, and all of the very highest ones are caused by atmospheric rivers and not other types of rain events. So that flood type is very important to knowing and estimating flood magnitudes and risk. The problem is that can create a lot of challenge when you try to like statistically determine what the recurrence interval is flood types, because you no longer have a single distribution of sort of the flood generating mechanism. You have these different things happening. So that's one reason. Also, we want more information on floods to be able to characterize shifts in flood types over time. And more granular detail also into the historical flood series will allow us to kind of assess flood impacts and risks associated with different types of floods. So what are we doing to build tools to help support this? For a few years now, we've had a joint project with funded by FEMA with the Army Corps and USGS, where we are looking to build data and advanced methods on these what we call mixed populations of flood types. So essentially more information on the type of flood. And this includes generating a benchmark data set of manually determined flood types through semi-automated classification methods, developing and testing new statistical methods, and then finally coming up with a plan for scaling this up to national scope. So we've been working in these kind of 6 pilot regions to start with now. And so we have a bunch of products and tools hopefully coming out over the next year or so. We're in the final year and the kind of dissemination year of this project. But we have a data set coming out this year that will have like 1,700 manually classified flood events where domain experts sort of did a detailed look back at historical weather maps and meteorological data to determine what type of flood it was, as well as what storm type was. So was it a rainfall flood caused by an atmospheric river? And so we hope this will kind of be a foundation for development of semi-automated and possibly machine learning methods too that can kind of scale up this type of determination of flood types. And just as a picture of that, so we have done some work on, applying that to 40 gauges within these basins and sort of automated classification of those. So this is just an example of how you could get a distribution of flood types of different stream gauges using these algorithms. And so primarily being advanced right now by the Army Corps through their Hydraulic Engineering Center, the HEC, their software. I plan to incorporate some of these methods in there. So they are actively working on figuring that out. And if you're familiar with the HEC SSP software, the statistical software, there's actually a page that describes this project and a lot of the products we're working on in that documentation. Okay, and then my last project I wanted to highlight was the stream flow drought forecasts. So this has been a project we've been working on for a few years, trying to address the sort of, that we have a kind of gap in our existing drought information where we can look at our existing products to see what the stream flow conditions are and which ones are kind of in drought, as well as kind of a more meteorological, more general drought forecast. But we don't have sort of detailed stream flow drought forecasts across the US available. And so this was an area that was highlighted that we might be able to fill in some additional data and tools to address. And so in this case, we want to I just want to note that we can define drought in lots of different ways. There's meteorological drought, agricultural drought. In this case, we're addressing stream flow drought. So that specifically when your stream flow kind of goes below a threshold that's considered in drought. The other thing we wanted to do was apply data-driven and machine learning models to determine the feasibility of forecasting drought onset, duration, and severity on the week to month time scale. And we specifically sort of went in with a data-driven modeling approach first to give us flexibility in trying out different data sets and modeling approaches in a kind of rapid manner. And we also wanted to not focus solely on natural flow regimes, but kind of more inclusively of regulated and unregulated stream flow areas. Kind of with an eye for comparing our performance against existing national scale models too. And so we want to end up kind of with this prototype operational drought forecasting tools that communicate both predictions and uncertainty. And we've been working with NIDIS and other groups to kind of guide that effort and coordinate with them. Okay, so our first effort was doing a pilot application in the Colorado River Basin, where we took kind of watershed average data such as precipitation, temperature, soil moisture, as well as static watershed attributes, and trained a long short-term memory neural network model to predict what the stream flow percentile was. And so from that, you can determine is the river in stream flow drought condition or not. And so that gave us kind of a baseline sense that this approach of kind of training a machine learning model to predict the stream flow percentile was worthwhile to go in, as opposed to other approaches such as trying to build like a general stream flow model and then use that to back out the drought. But this kind of like directly training a machine learning model on the transformed stream flow percentiles. And so we kind of learned from that initial pilot application. Worked with actually a student, a PhD student here at UVM to do some kind of evaluation on how well that model did. We just published that effort a few weeks ago. And kind of from that pilot application, we did realize we wanted to kind of reduce the complexity back from daily to weekly. That was a kind of big kind of decision point, just that stream flow drought isn't a fast changing phenomenon. So we decided to kind of back off to weekly resolution and build from there. So that approach for scaling up our stream flow drought work for all of the Catamounts US is now what's shown here, where we identified 3,200 stream gauges that have a relatively long and complete record. So thinking like we have like 95% or so complete data over the last 40 years. And that gives us a really solid like statistical foundation to describe what is low or high flow at those sites. And then kind of set up a whole data input workflow to capture meteorological forecast data as well as land surface data at all those locations. And from there, we are training models that, again, predict the stream flow percentiles at weekly forecast horizons from 1 out to 13 weeks. And from there, we can determine that kind of stream flow drought classification. Essentially, if the stream flow percentile is below 30%, we kind of consider that in like moderate drought. If it's below 20%, it's more severe drought, and so on. Kind of in a similar sense of what you would see on drought.gov. So again, very similar, like building from our baseline experiment. What we have kind of added in this scaling up to this operational forecasting is much more on the weather forecast data. So that has been a focus to bring in as model inputs. And we're also continuing to experiment with other data sets such as Landsat derived surface water extent and water use estimates for irrigation and public supply. And so we're excited now that these products are starting to be publicly available. We have sort of soft launched this tool, so it is publicly available, but we're just experimenting and making sure things are kind of running smoothly before the sort of full public announcement. And you'll see it, I'm sure, a lot more announcements of these drought tools as we get things kind of finalized here. But we have this web map, and again, I can pull this up afterwards if anyone wants to see. And that lets you kind of slide forward from 1 to 13 weeks and see the forecasts for stream flow drought conditions at those approximately 3,000 gauges across the US. It's been fun working on this with the what we call the VisLab team. They're in the USGS's water mission area headquarters, but they have some really great people that have expertise in designing graphics and interpretation of graphics. So we've kind of iterated a lot on how to convey a very kind of complicated prediction, in that we are predicting like a probabilistic stream flow percentile in a way that is somewhat clear and makes sense. So these are just some kind of snapshots of if you clicked on a certain gauge on that web map tool, this is kind of what the forecast looks like. We have some like iconography to indicate if that is a regulated river. There's prone to ice and those type of things. one of the kind of tricky things is that we train the model specifically on stream flow drought conditions. And so therefore, a lot of our predictions are biased towards the low end of stream flow. So we're not trying to predict all kind of stream flow conditions, but specifically when the river is low, that's when our forecasts are sort of like tuned specifically to address that. And so, yeah, just to summarize, the stream flow drought forecast provides a previously unavailable drought forecast and enables us to kind of have early warning capacity for that hydrological drought. So that tool, we're in the process of sort of coming up with a name for it. Stream flow drought assessment and forecasting tool seemed a little wordy. So we're thinking through different names for that. And continuing to experiment on the model, as well as kind of different ways to train and tweak that. So we actually have been experimenting with kind of a slightly different objective function and training data set for that just the last couple of weeks. So just to wrap up, some key takeaways here on the water conditions. I think this focus on development of a well-documented and open source package provides a nice, it serves as a consistent foundation for this next generation of water data services. And what's kind of new and exciting, I think it's both web-based and programmatic. And then on the hydrologic extremes data, these new benchmark data sets and toolings on flood types addresses a key limitation of our current flood data. So this will enable development of national scale approaches to characterize floods beyond just their magnitude. And then the adoption of data-driven models for the forecasting of stream flow drought allowed us to have a really flexible experimentation with data sources and application that I think would have been more challenging if we were developing a physics-based model or picking a particular modeling framework. So that effort, we're now seeing it provide some new early warning capacity at locations without existing forecasts. Yeah, hope that provided some insight as to the different kind of new tools we've been working on to provide water data on conditions and hydrologic extremes. Thanks. Happy to show, pull up a couple of those websites if useful, or answer any questions or chat about next directions.
Are you still using the same like flow metering devices that the USGS were able to use?
In terms of the stream gauging, like stations themselves? I mean, there's, so yes, certainly some stations continue to monitor with the same equipment. There's a whole kind of division of USGS, that's the operating system division, that focuses on looking at like new methodology for stream gauging. And so there's a lot of interest in camera-based methods right now. So I forget the terminology, but essentially using machine learning and other methods and like optical image processing to sort of track the flow velocity based on the camera, as opposed to kind of more direct measurements. So that's interest. I know there's a bunch of other technologies that they're looking at. So that is an area that the USGS is definitely doing a lot of experimentation on. And other sort of divisions of USGS are much more involved in that sort of physical measurement than I am.
That would be the large size particle velocity?
Yes.
Can you talk a little bit more about what kind of outcomes you hope to see from this work on characterizing the type of flood based off of peak discharge?
Yeah. So I think the the outcome that one of the main outcomes that we hope is that the analysis of flood risk, so that is often done by a flood frequency analysis, so determining like what magnitude the 100-year or annual exceedance probability for that magnitude flood would be. And that's done statistically, but that sort of, if essentially the current guidelines say if you have mixed populations, then that method is violated. And so you need to address that. And we currently don't have a sort of like federal guidelines on how to do that. And so one of that is the data was lacking. And so, individual stream gauges have been studied, but this is the sort of first kind of more national scale effort. And we hope that that then sets the foundation for coming up with a plan on making that operational, so that if you go in the future and pull flood data from USGS, it's not just the magnitude, like annual maximum flow, but you could get flood types as well. Yeah.
Well, I have two questions.
Sure.
One's sort of a question, and then there's a real question after. Do you know, or I guess others in the room know about the USGS Flow Academy? It's the question over here. Because that's where students can go to the hydrologic instrumentation facility, but I don't know when the application deadline
I've
is.
just
If you're
seen
curious
it,
about,
it looks really cool.
okay, so yeah, look up USGS Flow Academy. Applications might be closed for this year already. But if you want to learn more about instrumentation, it's a cool option. And then for the forecasts, what data sources are you using to look forward in time with the LSTM?
Yep, good question. So right now we are pulling in GEF's forecasts, as well as NMME seasonal forecasts. I think those are the two primary ones that are in the operational model. We've pulled some other ones that we've experimented with, but I think those are the two that we're sort of operationally pulling in.
Did you use those back in time for the LSTM batch size window or whatever it's called, or some combination of forcing data?
So yes, if in the
I should look at the paper.
that's okay. We do actually, it just came out this week, is the so the all the modeling details are in a journal article that actually just came out this week. And so the LSTM is using his his past antecedent meteorological data from NLDAS, as well as we're pulling in SWE, and then the forecasted meteorology would be coming from GEFS and NMME.
Okay.
And we use like the sort of reforecast periods to train that model.
Thanks.
Yeah. Any other questions?
I just wanted to give other people in the room a chance to ask. As you were talking, I was just reflecting on your time here at UVM, and especially the call that I had with the person who was considering hiring you. I'll tell the people in the room that that person at the time told me we really want to staff up at USGS on people with machine learning expertise. So I'm guessing that meant you were in the early wave, and that wasn't that long ago, right? 2021?
That was 2021, yes, or 2022.
So my question for you is, like, this was really impressive, and it's clear that there's a lot happening at USGS now on using machine learning. So I'm wondering, could you tell us a little bit about the evolution of staffing at USGS in that area? And also, could you talk to some of the students in the room about getting ready for that? Like, what could they do at UVM to get ready for that?
Yeah, so I was hired in a cohort of kind of joint modeling and data science or / machine learning folks. And so I will say even before that, I think there were a few people that had been doing some really state-of-the-art work on machine learning at USGS around stream temperature forecasting. And so we've continued to, I think, build on that expertise, but I work with some really, I think, top-notch people in terms of their machine learning expertise at USGS. And we do have, and I took advantage of some training courses. USGS, does not expect you to know everything when you come in. And so they offer a lot of onboarding and sort of career development. So we have a high performance computing center that does trainings on machine learning with the high performance computing. And we sort of have that, I think, capability split across like multiple, there's not like a machine learning or AI kind of data science division of USGS, but really it's spread across multiple offices. So there's people with the sort of machine learning specialist title in the modeling division, in the kind of like information dissemination division, as well as there's knowledge in the kind of more local offices, like the regional offices in New England. And we stay connected through different like communities of practice within USGS. That's been really effective. We've had a sort of machine learning working group that's met essentially monthly since I joined, and we discuss articles. We did a whole kind of year-long series on collectively compiling best practices that we're aware of and sort of put together kind of best practices guidance document. So yeah, those community practices have been one way that we've, I think, collectively like continued to try to stay on top of the very rapidly changing AI and machine learning out there.
And how about your advice for UVM students? And get themselves set up.
Yeah, I mean, so there's I took a machine learning course. It was called like Applied Artificial Neural Networks at UVM as a grad student. So that traditional courses are still available, and I think a great option. And I think those are of interest from people in different departments, not just like the engineering program that I went through. But I think there's more opportunities now for like data science and machine learning focused workshops in the hydrological sciences through like Quasi and AGU. I certainly have seen those more over the last few years of sort of like workshops specifically targeting machine learning. So I would keep an eye out for those type of things. I personally have found some of the sort of science workshops that I kind of stumbled into. Some of the most sort of like impactful in terms of gaining connection and networks to people and skill building. So those workshops, keep an open eye out and be willing to maybe go to workshops that seem a little bit outside your knowledge base.
I have a Zoom question.
Yes.
What projects on the horizon are you most excited about?
Yeah, I think so. I think we're all really excited to see the kind of next steps for the flood typing work, and some of that means we now get to, I think about dissemination and sharing that with the public, and how to make that more useful, and talk about ways to make that operational. So that's been really, I think, enjoyable, exciting to work on. I personally am also on some other projects that I didn't share today that I'm excited about, doing some work on post-wildfire water quality with Brian Ebel, who's also located here. So that's another area that I think there's a lot of interest in, and I'm excited to develop some methods more on that project as well.
You brought up a really great point, I think, halfway through your presentation where you showed the regression quantiles, or the set off the top. Your work has me really excited. I work a lot in water quality, and a number of times we'll get discharge observations without any information, and we don't know, like you get a high flow but low turbidity, is snowmelt, presumably, right? Or being able to characterize outliers with accurate stream flow conditions is going to be quite impactful,
Yes.
especially for the sediment regressions and such.
Thanks for bringing that up, because I came into that project much more with like a water quality background than a flood frequency analysis background. And I think the focus on the project was the flood frequency, but I was interested in that for the connections to the water quality side, because I've done a lot of work at the sort of like event scale and looking at water quality loading and things. And I think flood typing is or storm typing in general is like very applicable to that area as well.
That's great work.
Right.
For the flood typing, I think it said semi-automated.
Yes.
What's automated and what's manual in that?
Yeah, that's a good question. I think the semi-automated, let me skip back here. The semi-automated refers to that, we on this project have still been sort of like using domain expertise to kind of select and design the kind of like decision tree and like identification of thresholds that make it this type or that type. So it's not that you can go to a new stream gauge and sort of click run on an algorithm, but more you would want to, right now it's like someone would expand to a new area, but then check that the thresholds and things are making sense and do some validation and like then apply the algorithm to the whole kind of time series. So that's the kind of semi-automated part. The project didn't explicitly include kind of like a machine learning development piece, but we have been definitely keeping an eye towards making sure that work we're doing is useful if we want to try out a much more sort of like data-driven or automated approach to classification. So that's an area that myself and another scientist in the project have been sort of exploring on the side as we go.
And one more.
Yeah.
This is from Matt Vaughn. Hi Scott, great talk. Exciting to see these new tools. Can you talk about the decision to release high swap in Python versus R? I've been happily using the USGS package in R for years. I'm wondering if this is part of a large trend at USGS and if there is a plan for an R version / wrapper. Thanks, Matt.
Yes, that's a great question, Matt. And it's, I will say I asked that question myself when I joined that project of like, why are we kind of switching to Python when we have existing R packages that it would complement? And so one, I think USGS has been sort of within the kind of water mission area trying to be more, I'd say, I don't know, language agnostic with a lot of tools. So have options in both R and Python. We do have some capability both in Python and R for these type of statistics. There is a package called HASP that was more groundwater focused, but it has a lot of the same capability as HiSwap. That is an R Shiny based package. So we do have some capability in both, but I think it was why it was Python was a little bit more that there was interest in it being used in a web services kind of operationally, and that pushed it more towards development in Python. If it was focused more on the sort of like hydrologist using it on their desktop, I think it would have been developed in R. But because we wanted that package, integrated into the sort of operational software stack that is running, that lends itself much more to Python packages just being easier to integrate often. A lot of the Amazon Web Services are just easier to work in with like Python than R.
Anything else on Zoom?
Must have makes sense, thanks.
Last chance in the room.
Oh, you brought up, you said water quality background. Okay, so I like your approach. Do you think it would be possible, and we'll just kind of keep it at a high level, with enough data to predict a good observation? So here you're predicting a flood, a type of flood. If we had enough data, could we possibly use these informed machine models to say that's an algorithmically approved data point versus our provisional status right now, right? When you go to USGS, you see provisional data. I'm going through your PowerPoint, and in the field that I work in, we have just data exhaust. Throwing all these beautiful data points away that could potentially say, good point to go into your package. I was curious if you could talk about it. You introduced water quality, so I figured I'd kind of crack it open.
There very much are, I have not directly been working on it myself, but there very much are efforts to do that. There's actually a PhD student defending tomorrow that has been working, EJAS, has been working on sort of automated machine learning for detecting anomalies in records and kind of automatically flagging those. And has been connecting to folks in the USGS observation system division that sort of comes up with a methodology for that. And they have also been working on that. There definitely are automated methods for flagging anomalous data that are being tested. And I think those will be used definitely going forward.
Excellent.
I agree. It is a kind of an important issue.
Yeah.
Is there other Zoom questions? Anybody else in the room? All right, this is a great turnout for the first seminar of the semester. The Alumni Association dropped by to leave a gift for you because they want to be sure the world knows how great UVM alumni are. They're doing impactful water work. And we have also stuffed the bag with a bunch of WRI swag.
Oh, thank you. Yeah, thank you all for coming.
Yeah, thanks for doing the first seminar. Were you going to say something?
I was going to say, I work over in the office here, and so, yeah, I'm
So
fine.
any of you who want to come back, come every Monday that we have one of these. We'd love to see more people here. We have goodies on the table over there, so don't rush away. Grab an apple and a cookie and hang out and talk to Scott. And come back in the next following weeks. We don't have one next week, but we have one in a few weeks, thanks to Hannah and our interns, Olivia, where's Olivia? And Emily probably had some role in this in helping organize these, and we'd really like to create this culture of come in person and spend some time eating snacks and connecting with each other. Thanks a lot, Scott.
Thank you.